Dear students, welcome to the next lecture of Geomatics Module 1 Traverse Surveying. So far we learned what is traverse surveying, what are the different methods of traversing, what is latitude, what is departure, what do you mean by closing error, what are the checks that can be done to check the accuracy of the closed traverse, and how to compute the traverse. Different traverse computations we learned. Moving on to the last topic, that is balancing the traverse, its different methods. Balancing the traverse. So far you learned how to measure the error, that is our closing error of a closed traverse. So once if you know what is the error in a particular traverse, you can correct it using different methods. So such methods are termed as balancing the traverse. So the term balancing is generally applied to the operations of applying corrections to latitudes and departures so that summation of latitude will be equal to 0 and summation of departure will also be equal to 0 so that we get a perfect traverse. So this is applied only if the survey is a survey forms a closed polygon, or we can say if it is a closed traverse. So let us see what are the different methods. The following are the common methods of adjusting a traverse. First one, Baudit's method. Second, transit method. Third, graphical method. And fourth is axis method. So we will see the detailing of the four different methods. Before that, the first two methods, that is Baudit's and transit method, are analytical method. Okay, we have certain computations or equations, from that numerical calculations we are sorting it down. But the next two, that is the last two methods, that is graphical and axis method, are graphical methods. We are not computing anything or we are not calculating anything, we are just drawing certain figures and we are solving the issue. Okay, so first two methods are analytical and the last two are graphical method. So first method, that is Baudit's method. This method has certain assumptions. Let us see what it is. The basis of this method is on the assumptions that, first one, errors in linear measurements are proportional to root L. Okay, errors in linear measurements are proportional to root L, and errors in the angular measurements are inversely proportional to root L. What is this L? L is the length of a line, means there will be a traversing like A, B, C, D, E, A. It is a type of traverse, right? So AB is a particular length. So whenever we are computing the error of that particular length, for example, if it is AB, that error will be, if it is linear error in linear measurement, it will be directly proportional to the root of L. If L is 25 meter, then the error of linear measurement will be proportional to root L, that is 5. And error in angular measurement will be inversely proportional to root L. These are the two assumptions made in Baudit's method. Okay, this method is also termed as compass rule method, and it is mostly used to balance the traverse where linear and angular measurements are of equal precision. Whenever we are taking this method, we will just check whether the linear and angular measurements are taken properly or not, whether it is precise. In such cases, this method can be easily adopted so that we get good results. Okay, the total error in latitude and departure is distributed in proportion to the length of the sides. Please note this because it is different for the next method. So here we are calculating the error and we are distributing in proportion to the length of the sides. So that will be obviously reflected in our equation. We will see what is the equation for Baudit's rule. The equation for Baudit's rule is correction to latitude or departure of any side equal to total error in latitude or departure into length of that side by perimeter of traverse. This equation is important. You have to study it by heart because you will get problems to solve with this, either with this method or either with transit method. So you have to study the equation. So keep it in your mind that correction, if you are doing correction for latitude, so correction to latitude of particular side AB will be equal to total error in latitude into length of that side by perimeter of the total traverse. Otherwise, if we are doing it for departure, we will correction for that departure will be total error in, you have to take the departure into the rest is same length of that side by perimeter of traverse. Okay, so please write this equation in your book. So in the next class we can solve the problems. So briefly it is written the equation. So we will see what is CL. CL is the correction to latitude of any side, and CD is correction to departure of any side, and sigma L is total error in latitude, sigma D obviously total error in departure, and sigma small l equal to length of the perimeter, and small l is length of any side. Okay, so these are the notations. So when converting our equations into the symbol, we can write it as CL equal to sigma L or summation L into small l by summation L, and CD equal to summation D into L by summation L. Just keep it in your mind. The right side is same, like L by summation L, length by perimeter. Here if it is latitude, you have to keep the error in latitude. If you are doing correction for departure, you have to keep total error in departure. And second method is transit method. Okay, this method is used when angular measurements are more precise. As I used to tell you, for many public exams this question is generally asked. Which is the method preferred if angular measurements are more precise? Which method is used for balancing the traverse? So the answer is transit method. Okay, and here the total error in latitude and in departure is distributed in proportion to the latitude and departure of sides, not in terms of length. In the other method it was in proportion to the length of that side. Here we are distributing in proportion to the latitude and departure of sides. Okay, and here angles are less affected by corrections applied by transit method than by Baudit's method, and the equation is, transit rule is, you can see the equation, if you are doing correction to latitude of any side, then it is equal to total error in latitude, same as the previous equation, into, there is a difference, latitude of that line by arithmetic sum of latitudes. Okay, in the previous it was length by perimeter. Here we are distributing the error in terms of its latitude or departure. So instead of the length, we are giving the latitude of that line by arithmetic sum of latitudes. Okay, and in case of departure, correction to departure of any side will be equal to total error in departure by, total error in departure into departure of that line by arithmetic sum of departures. Okay, please understand why it is written in brackets. If you are talking about latitude, it will be the equation, and if you are talking about the departure, you have to replace all latitude with departure. When expressing in symbol terms, CL is the correction to latitude, CD is the correction to departure, summation L, capital L is equal to total error in latitude, summation capital D, total error in departure, LT, okay, L suffix T is arithmetic sum of latitude, DT equal to arithmetic sum of departure, capital L latitude of any line, capital D departure of any line. So the equation will be CL equal to summation L into L by, actually just LT is required because LT itself is arithmetic sum of latitude. Okay, so no need of that summation, but if you understand, it's okay. Okay, if any doubt you have, we can clear it in the next class. Similarly, for departure also the equation is given. So that is all about Baudit's method and transit method. Before moving on to the graphical method, we have a certain comparison between Bowdit's rule and transit rule. Let us see what it is. Bowdit's rule is particularly useful for a compass traverse where the angles are susceptible to considerable error. Okay, Bowdit's rule are mostly used for compass traverse. Okay, and where the transit rule is more suited for a theodolite traverse where the possibility of error is more in the linear than in the angular measurements. Whenever we have angular measurements precise, if it is precise measurement, if angular measurements are so accurate, then we prefer transit rule as mentioned before. Okay, since it is logical to presume more error in the linear measurements, the transit rule is better acceptable than the Bowdit's rule. Okay, comparing both the rules, we are preferring transit rule because we know more errors will be susceptible to the linear measurements. That's why. And in general, it can be concluded that Bowdit's rule alters the adjusted bearings more, whereas transit rule alter the distances more. Okay. So moving on to the third method, that is graphical method. As I said earlier, no such computations or equations are not there in this type of method. We are just figuring out the survey and we are applying some scales and we are plotting it so that the closing error can be neglected and we will get the correct traverse. So this is used for rough survey such as compass traverse because it obviously it is not that accurate and this Bowditch rule is applied graphically. Okay, the same Bowditch rule is applied graphically, so that's why this method is also called as Bowditch's graphical method. Okay, according to this method, it is not necessary to calculate latitudes and departures. We are not going to calculate anything over here. Okay, so before plotting the traverse directly from the field notes, the angles or bearings may be adjusted to satisfy the geometric conditions of the traverse. If such small errors are there in angles, that will be adjusted before plotting it to the our drawing paper. Okay, so see the figure. Here the figure, the survey, the actual traversing is given as our A, B dash, C dash, D dash, E dash, A dash. Okay, so this is the actual traverse. So here A is the starting point. It continued to B dash, C dash, D dash, E dash and ended up at A dash. So it didn't complete the traverse. Okay, the starting point is A and it ended up in some other point, that is A dash. So there is an error, that is our closing error, which is marked in the figure as E. Okay, so you have to adjust that A dash should be shifted to the point A. Okay, so the initial figure is just A, B dash, C dash, D dash, E dash and A dash. Okay, make it clear. We will see the procedure how to adjust this closing error. Procedure. So from figure A, polygon A, B dash, C dash, D dash, E dash, A dash represents an unbalanced traverse having a closing error equal to A dash, since first point A and last point A dash are not coinciding. This is already explained. I hope it is clear. So the total closing error, that is A dash, is distributed linearly to all sides in proportion to their length by a graphical construction as shown in figure B. Okay, so A dash is our closing error. So this is going to be distributed equally in, not equally, proportionally to all other sides. Okay, so for that, see the figure B. Okay, so here figure B, we have this A dash line we have, right? A dash length we know, so that will be plotted first, and we know what is E. What is E? Closing error. That length is also known. So from the right point, that is A dash, you will draw E. If it is 1.25 meter, you will be drawing a vertical line so that you will that distance is measured and that is drawn, so that it will reach up to small a. Okay, so a dash is from the right end you have drawn 1 point, for example if it is 1.25 meter, that much distance is drawn upwards and you got the point small a. Now the small a and capital A is joined to form a triangle. Okay, now you have formed a triangle, that is a dash small a. Okay, so after this you can plot the length. You can see a b dash, b dash c dash, c dash d dash, d dash e dash and e dash a dash. Okay, these represents the length of sides of traverse either to the same scale as that of figure A or to a reduced scale. Imagine if you have a b dash length is 5 meter, that you can reduce into 5 centimeter and you can draw over here a b dash 5 centimeter. Similarly, each side length is represented over this baseline of our triangle. Okay, so these points are already plotted. Now the ordinate a dash is made equal to the closing error a dash of figure A. Okay, so you are going to construct some similar triangles. Okay, so after that you will just join whatever points are there. We have b dash, c dash, d dash, e dash you have. You will just join that point to that hypotenuse, that sloping side of our triangle. So you will get small b, small c, small d, small e and small a. Okay. So by constructing this similar triangles, the corresponding errors small b dash, small c capital C dash, small d capital D dash, small e capital E dash are found. Okay, so you got the error that has to be distributed for each line. So in figure A, now you have to look the figure A. In figure A, lines E dash E, D dash D, C dash C, B dash B. Okay, these are drawn parallel to the closing error A dash A and made equal to E dash, D dash, C dash and small b dash respectively. Okay, so after getting these values, that is small b capital B dash, small c capital C dash, etc., you can draw just in the figure A. If you see, you can you just draw from point E dash. You are going to draw that much distance inwards parallel to our closing error. So you will get capital E. Similarly, at D dash, you are going to draw a line and reach capital D, C dash to C and B dash to B, so that you will get the polygon A, B, C, D, E. This obtained polygon represents the adjusted traverse. Okay, it should be remembered that the ordinates b small b capital B dash, C dash, D dash, E dash, A dash of figure B represent the corresponding errors in magnitude only but not in direction. That's why we are drawing it parallelly to the closing error. Okay, so that you will get the adjusted traverse. Okay, I hope it is clear. If it is not clear, please hear this video again. Please repeatedly hear this again. Still, if there is any doubt, I will be explaining in our next live lecture, so that I can draw lively. I can draw it and show you how these figures are coming. Okay, just have a rough idea, or if you are getting it, it's good. But if at least you have to get rough idea, so that it can be cleared. If any doubts are there, it can be cleared in our next live lecture. Okay. The last method is axis method. The method is adopted when the angles are measured very accurately, the corrections being applied to lengths only. So whenever we are doing the surveying with good precise measurements in angular measurements, then we go for this axis method, which is again a graphical method. So it is having few limitations, but still it is easy to conduct this type of method. Here only directions of the line are unchanged and the general shape of the diagram is preserved. To adjust the closing error A1 of a traverse ABCDEFA1, following procedure is adopted. Let us see the figure first. In this figure, small letters A, B, C, D, E, F, A1. This is the actual traverse. So obviously the initial point and the last point is not coinciding. So there an error exists, that is closing error, that is of A1. Okay. So to adjust this, first you have to join this A1A. Okay. You have to join A1A and produce it to cut the side small CD in X. Okay. You have to join A1A and you have to prolong the line so that it will touch the other side, that is the side CD, and that point is small x. The line A1X, this is known as the axis of adjustment. Okay, this axis divides the traverse into two parts, that is small ABCX, that is one part, and the other part is A1FEDX, that is the other part. Okay, so after dividing into two parts, you have to bisect A1A in A. You have to divide A1A into two parts and the midpoint is marked as capital A. Okay. Now you have to join X to B. Okay. You have different sides. So you are going to join XB and you are prolonging the line, and you will join XFXE and you will be prolonging, and XF. Okay, you have joined XB, XE and XF. Through A, draw a line AB parallel to small ab cutting XB produced in B. So the next step is just note down the point capital A. From the point A, you are going to draw a line parallel to small AB. Okay, please, whenever I am saying this, just see the figure. You are going to draw a line parallel to small ab. You are drawing the line capital AB, so that you have to end it up. You have to end it up at a point which will coincide with this prolonged line from XB. Okay, so that you will get capital B. Okay, again you are going to draw through capital B, which is a line parallel to the small bc. You are drawing capital BC parallel to small bc, and you have to end up in the point capital C, which is the prolongation of small xc. Okay, so you got the points capital A, capital B and capital C. So you got 3 points of the first part. Okay. Similarly, you are going to draw backwards. Okay, through A, you are going to draw AF, capital AF parallel to small a1f to cut XF in capital F. Okay, you are drawing parallel a line to the A1F, so that A1F and the parallel line to the A1F and XF line will intersect at a particular point, which is our capital F. Okay, so this step is repeated again through capital F. We are drawing FE parallel to small fe to cut XE in E. Okay, again through E, draw ED parallel to small ed to cut XD in capital D. Okay, so you got all the points, that is capital A, B, C, D, E, F, which is the adjusted traverse. You got the line. You got the traverse. Okay, so for certain equations, for certain calculations, you can if you want to do corrections. Okay, if you want to do corrections to small a b, okay, for that equation has been derived. For that one derivation is required, that is just check the triangle capital ABX and small triangle small ABX. Okay, so when comparing these two triangles, you can say capital AB by small ab equal to capital AX by small ax. Okay, so from that you will get capital AB equal to capital AX by small ax into small ab. Okay, so you got the equation. So for correction to small ab is capital AB minus small ab. Capital AB minus small ab. Now you are going to substitute the value equation, the above equation for capital AB. In the above equation is given AB equal to AX by small ax into AB. That has been substituted here, minus AB equal to, and we are taking the small ab outside, out the brackets, and AB into capital AX by small ax minus 1. Okay, and just doing simple mathematics, you will get AB small ab into capital AX minus small ax by small ax. Okay, what is this capital AX minus small ax? Just see the figure. Capital AX minus small ax is half of the closing error. Okay, half of the closing error. So that has been substituted, that is AB into half closing error by AX. So from this, a general equation can be derived, that is correction to any length equal to that length into half closing error by length of axis. Okay, correction to any length equal to that length into half closing error by length of axis. So this is the axis method. So as I said, for graphical method, have an idea about this. Please write down these equations and draw these figures into your notebook. This will be explained again in our live class, so that it will be easy for you to understand. Okay, so in the live class I can just draw you and show each step what is happening. Okay, so before that you should have some idea. If you have grabbed everything, it is fine. Okay, so if you please collect all your doubts and be ready to ask in our next live lecture. Okay, so thank you so much for listening.